Rocket launches are among humanity's most awe-inspiring achievements, but their effects on Earth go beyond what's visible. Each launch releases a cocktail of gases and particles into the atmosphere, some of which pose serious environmental concerns. One major question scientists continue to study is how much radiation, if any, reaches Earth after these powerful liftoffs. Most rockets emit primarily non-ionizing radiation like infrared and microwave, which doesn't penetrate Earth's surface or harm living organisms. However, ionizing radiation from cosmic rays and charged particles can become more relevant in the upper atmosphere. During launches, some rockets pass through the Van Allen radiation belts, disturbing charged particles and potentially altering radiation exposure in the surrounding atmosphere. Yet, the majority of this radiation remains confined to space, far above the layers where humans and animals live. The most pressing issue tied to launches isn't direct radiation, but indirect effects from rocket emissions interacting with the stratosphere. Rocket engines release aluminum oxide particles, soot and chlorine compounds that can deplete ozone and trap heat. These compounds create chemical reactions in the stratosphere, potentially weakening the ozone layer that shields Earth from harmful ultraviolet radiation. If the ozone layer thins, Earth's surface may face increased UV levels, indirectly impacting both human and animal health. Increased UV radiation can affect animals in subtle but damaging ways, such as impairing vision, reducing fertility, and weakening immune responses. Amphibians, for example, are particularly sensitive to UV radiation, with studies linking increased exposure to declining populations. In marine environments, UV damage can disrupt plankton populations, which form the base of the food chain for many aquatic species. Animals living at high altitudes or near the poles are also more vulnerable due to thinner natural ozone coverage. As rocket traffic increases, so does concern about cumulative impacts on global UV levels and climate systems. A 2010 study published in Geophysical Research Letters warned that frequent launches using solid fuel rockets could significantly harm ozone levels. Solid fuels often contain perchlorates, which release reactive chlorine that accelerates ozone breakdown in the stratosphere. In contrast, liquid fuel rockets tend to have fewer ozone-depleting emissions, but still release CO2 and other pollutants. Even reusable rockets like SpaceX's Falcon 9 produce emissions that accumulate over time, especially when launch frequency rises. While most launches release emissions high in the stratosphere, they don't stay isolated and can descend into lower layers through atmospheric mixing. Additionally, black carbon particles from rocket exhaust absorb solar energy and contribute to localized heating in the upper atmosphere. This heating may disrupt weather patterns or amplify global warming effects in vulnerable regions. Although emissions per launch are relatively small compared to other industries, the altitude at which they occur amplifies their impact. The environmental footprint of a single launch can persist for months, especially if multiple launches follow in quick succession. There's also concern over space tourism, increasing launch frequency with minimal environmental regulation in place. Some companies propose suborbital flights daily, multiplying emissions without sufficient understanding of their long-term effects. Agencies like NASA and the FAA are beginning to examine the environmental costs of launching rockets at scale. Studies suggest that rocket emissions could contribute to regional climate shifts if not addressed through better design and policy. To address these concerns, scientists are exploring alternative propellants that emit fewer pollutants and generate less stratospheric disruption. Methane-based engines like those used in SpaceX's Starship produce fewer soot particles than kerosene-fueled rockets. However, methane is still a potent greenhouse gas and requires careful handling to prevent leaks during launch and fueling. Other innovations include hydrogen-powered engines, which emit mainly water vapor, but face challenges like cost and storage complexity. Some startups are even developing electric propulsion systems for small satellite launches, which could drastically cut emissions. Yet, these technologies are still in development and may not scale quickly enough to offset emissions from conventional launches. Improved nozzle design and emission scrubbing systems are also being tested to limit the release of harmful compounds. Ground facilities can also adopt cleaner fueling practices to reduce the environmental footprint before rockets even lift off. Another area of interest is the frequency and timing of launches, as these factors influence how emissions affect atmospheric chemistry. Launches during certain seasons or times of day could minimize ozone disruption based on stratospheric circulation patterns. Modeling studies show that even small changes in launch schedules might mitigate ozone loss if planned strategically. International coordination is essential since rocket launches occur around the globe and their emissions don't respect national boundaries. The Intergovernmental Panel on Climate Change, IPCC, has acknowledged the need to study aerospace emissions more closely in its reports. Space agencies like ESA and JAXA are contributing data on high-altitude emissions to build a clearer global picture. Environmental organizations are also pushing for stricter oversight and independent impact assessments before launch permits are approved. Despite growing awareness, regulatory frameworks often lag behind the pace of aerospace innovation, leaving many gaps in enforcement. This creates an urgent need for updated policies that reflect both the promise and risks of increased space activity. In particular, launch-heavy regions like Florida's Space Coast face localized ecological threats from increased emissions and noise pollution. Wildlife in these areas may suffer from habitat disruption, chemical exposure, and stress caused by repeated sonic booms. Seabirds nesting near launch sites can be startled or disoriented, reducing breeding success and altering migration behaviors. Manatees, dolphins, and fish in nearby waters may experience sensory interference from low-frequency sounds and waterborne vibrations. These effects compound over time, especially when launch activity becomes routine and unregulated. Recovery for affected animal populations may take years or remain incomplete if launches continue without mitigation. The challenge lies in balancing technological advancement with environmental preservation, a task that demands collaboration across science, policy, and industry. SpaceX, Blue Origin, and other commercial players are now under scrutiny for the cumulative environmental impacts of their missions. Government agencies must work swiftly to ensure that innovation doesn't outpace safeguards for Earth's atmosphere and ecosystems. Better data collection, transparent reporting, and public access to impact studies can help drive accountability in the aerospace sector. Open access to emissions tracking and radiation monitoring will allow independent scientists to verify industry claims and inform public debate. Collaboration with ecologists can help design launch protocols that minimize harm to sensitive animal habitats. For instance, excluding launch windows during nesting or breeding seasons could protect vulnerable species from unnecessary stress. Wildlife monitoring stations near launch pads can detect changes in behavior and health metrics over time. Some programs even use satellite tracking to study how large mammals respond to recurring noise from rocket tests. These findings can guide mitigation strategies like vegetative sound barriers or limited nighttime launch schedules. In the long term, global standards for spaceport construction and launch operations will be needed to protect biodiversity. If space activity becomes as common as air travel, its environmental footprint must be managed accordingly. That means applying the same scrutiny to rockets as we do to cars, planes, and ships in terms of emissions. Education campaigns can also raise awareness among space enthusiasts about the hidden costs of frequent launches. Citizen science projects can empower people to collect radiation data and contribute to real-time environmental monitoring. These initiatives help bridge the gap between scientific research and public engagement on aerospace sustainability. Schools can integrate lessons about rocket science and environmental stewardship to inspire future innovators with an ethical foundation. Artists and filmmakers can shape public perception by highlighting both the marvel and the impact of spaceflight. Documentaries and short videos can visualize the unseen consequences of launches, making them more relatable and urgent. Conferences like COP or the UN climate summits can spotlight aerospace emissions as a key agenda item. Symposia can delve into specialized themes, such as radiation impacts from aerospace activities on Earth's ecosystems. Technical panels can review advances in materials that reduce radiation and chemical emissions during launches. Government agencies can establish task forces to regulate rocket emissions and enforce environmental compliance. Environmental NGOs can advocate for stronger policies and support research into launch-related pollution. Partnerships between industry and academia can accelerate the development of low-radiation propulsion systems. Open innovation platforms can crowdsource ideas for reducing spaceflight-related atmospheric damage. Hackathons and design challenges can stimulate creative engineering solutions to current aerospace environmental problems. Media coverage can play a role in holding companies accountable for the ecological footprints of their launches. Transparency reports detailing radiation, emissions, and fuel types can encourage responsible industry behavior. Real-time environmental monitoring dashboards can help the public stay informed about atmospheric changes during launches. Climate activists can use data to advocate for reforms in how and when launches are conducted. Space tourism, an emerging trend, will further increase the frequency of launches and emissions over time. As this industry grows, so too will its contribution to high-altitude radiation and ozone depletion risks. Without regulation, commercial space travel may amplify the environmental consequences of today's traditional rocket launches. The long-term effects of cumulative stratospheric pollution could push Earth's climate systems into unstable territory. Experts caution that, if left unchecked, rocket emissions could eventually rival aviation's role in climate change. Space agencies are now investing in alternatives like methane-fueled rockets, which release fewer soot particles. Methane, while still a greenhouse gas, results in less stratospheric black carbon compared to kerosene-based fuels. Hybrid rocket engines, combining solid and liquid propellants, are also being explored for their potential environmental benefits. Advanced modeling shows that even small reductions in upper atmosphere emissions can yield measurable global climate benefits. By minimizing the black carbon load in the stratosphere, we can reduce localized heating and ozone disruption. Launch timing is another factor. Scheduling launches during less sensitive atmospheric conditions may help mitigate impacts. Launch angles and trajectories can also be optimized to limit high-altitude pollution concentrations over populated areas. The question isn't whether we should launch rockets, it's how to launch them without poisoning our skies. The space race must now include a race for sustainability, driven by science, ethics, and innovation. Because when it comes to protecting Earth from space radiation, the real challenge begins right here on the ground.